Hello and welcome to Discrete Math for Computer Scientists. My name is Kachik and this is the third lecture of the series. Today we're going to be talking about the multiplication rule, which is an important technique for accounting in combinatorics. The definition of the multiplication rule is as follows. If a procedure can be broken down into k independent steps, and the first step can be performed in n1 ways, the second step can be performed in n2 ways, regardless of how the previous steps are performed, all the way to the kth step, which can be done in nk ways, regardless of how all the preceding steps were done beforehand. Then the entire procedure can be done in n1 times n2 times so on and so forth, nk ways. So for the first problem, we can use this technique. Given two sets m and n, how many ordered pairs A and B are possible where A belongs to M and B belongs to N? So when using cardinalities for these sets, this becomes very simple. So step one is choose an element for A. Right? This can be done in M ways. Step two, choose element for B, which can be done in n ways, cardinality of n. Thus the total number of possible ordered pairs is m times n. Simple. A more applicable problem here is a deli offers 3 types of bread and 5 kinds of fillings for sandwiches. How many types of sandwiches can be made? So breaking this down into steps again. Step 1, choose bread. We have 3 ways we can do that. Step 2, choose filling. Here we have 5 ways we can do that. So by the multiplication rule, we get 3 times 5 equals 15 possible choices for our sandwiches. If this needs more convincing, please use the tree diagram from last lecture. Problem 3. Chairs in an auditorium are to be labeled with an uppercase letter and a positive integer less than or equal to 100. What is the largest number of chairs that can be labeled differently? Well, step 1. Let's choose an uppercase letter. Here we have 26 choices. In step 2, we have to choose a positive integer less than or equal to 100. How many choices do we have there? So we have between 1 and 100, right? And by the rule from lecture 2, we have 100 options here. So this gives us 26 times 100 equals 2,600 total possibilities for chair labels. Problem 3 is a little more sophisticated. The question is, a pin is a sequence of 4 symbols from 26 letters from the alphabet and 10 single digits. How many pins are possible? That's the first step. The second step asks, what if repetition is not allowed? So let's answer part 1. In part 1, you can see step 1 is choose first digit. We could actually repeat this and do the same below. So we have step 2, choose the second digit, 3, third digit, and 4, fourth digit. And for each of these steps, we are left with a possibility of 26, since we have 26 letters, and plus 10, since we have that many possible digits. So 36, 36, 36, 36 is your answer. So it's 36 times 36 times 36 times 36, which leads us to 36 to the fourth as the answer. Let's add another page for part 2. So part 2 asks, what if we do the same thing, but without repetition? Let's copy this part from before. So the difference here is these counts will change, but the steps remain the same. So the first choice, for the first digit, we have 36 options. The second, we have 35 because we are left with one less option, and that one less option is the one we chose for the first step. Following this logic, we have 34 for the next, since now steps 1 and 2 have taken 2 of those options, and 33 for the last. So the final answer is 36 times 35 times 34 times 33 total pin options for part 2. Another more complicated problem here. So we have 3 offices for president, treasurer, and secretary. And these must be chosen among the people Ann, Bob, Chris, and Dan. Ann cannot be president, which is an additional constraint, and Clyde or Dan must be the secretary. So how many ways can the office be filled? So using what we have above, we'll try something which we'll call attempt 1. Attempt 1, first step. Let's keep it simple. Choose P. Here we'll say P is president. Choose P for president. Step 2, choose treasurer. Sure. Step 3. Step 3, choose secretary. So the first problem that we have with this attempt so in the first step for president, we know that N cannot be president, so we have 3 choices here. For treasurer, we have any options except 1 because we chose president, so that's 3. For secretary, we're left with either Clyde or Dan, so that's 2 options, so we have 3 times 3 times 2 equals 18, except this approach is wrong. Let's talk about why. The reason why this approach is wrong is because step 3 depends on steps 1 and 2. And before in the multiplication rule, we said that the preceding step should be independent of the current step. Why is it dependent? Let's say that on steps 1 and 2, or 1 or 2, we chose Clyde or Dan. What that means is step 3 will not have the option available to choose from, which means the number 2 here will be 1 or 0, depending on who was chosen for president or who was chosen for treasurer. So let's try another attempt here. Attempt 2. Let's reframe the problem for attempt 2. We can instead have step 1 be choose. Let's do choose secretary. And step 2, choose president. Step 3, choose the treasurer. So you might be thinking, how is this any different? Well, for secretary, we have 2 options. For president, we have 2 options as well, independent of who is chosen for secretary. This is because we know Anne can't be president, and we know that one of the people chosen above, independent of Clyde or Dan, will limit the number of people who can be president by an additional 1, which leaves us with 4 minus 2 equals 2 people left here. And for treasurer, anybody could be treasurer. This is left with 2 people here. So the number of outcomes we have is 2 times 2 times 2, or 8. And this actually gives us the correct answer. Tip. Let's try to remember this. Start with the most restrictive step first. This is a huge, huge, huge tip, and it will always be relevant when using the multiplication rule. Another problem, problem 5. Recall that the power set is all possible subsets of set S. If S equals this set here, what is the cardinality, or the size of the power set? How we could do this is by breaking down this into steps. Let's call it n steps, or step 1 is we choose if xi is in the subset. In xi, here I denotes a number between 1 and n. Step 2, choose if x, should have put 1, 2 is in the subset. This goes down to step n, choose if xn is in. So this is a clever way to reframe the problem, where now we break this down to 2 times 2 times 2, dot, 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 all the way to times 2, where here is n choices, or n steps we made, one for each element in the subset, or the set x, excuse me. This is the same thing as 2 to the power of n, which is our final answer. Moving on to a much more difficult problem. How many odd numbers are between 1,000 and 9,999 with distinctive digits? Let's start with attempt 1. We can do step 1, choose. Let's choose the first digit. Step 2, choose the second digit. Step 3, choose the third digit. Step 4, choose the fourth digit. So let's keep these the same. Let's keep these the same. So quickly you could see that we have a problem here. Because we're looking at odd numbers, the number should end in a 1, 3, 5, 7, or 9. But because the digits must be distinct from one another, the number of elements to choose from in step 4 depends on the previous steps, which is a no-no for the multiplication rule. For example, if in step 3 we chose the number of 1. Let's say in steps 1 we chose 2, steps 2 we chose 4. So now we're left with one less option here. But step 3 we could have chosen 6, and we could have had 5 options total. So you can see quickly that this approach would not work. Let's try a separate attempt. Here instead, we can think about the restrictive tip that we had, where we choose the most restrictive option first. What that means is choose the fourth digit first. Then we could do what we had before, or we can work our way down, choose third, it's 3, choose second, it's 4, choose first. So the reason why this attempt is incorrect or wrong is much more subtle than attempt 1. Choosing the fourth digit first actually is correct, and that's because we are left with the same 5 options for the odd digit regardless. However, if you work your way down, the last step, choosing the first digit, we have the options from 1 to 9, but not 0. So what this means is if 0 was chosen beforehand in steps 2 or 3, then we have options 1 to 9 minus the 3 digits we have before it because it's distinct. So what that means is 9 minus 1 plus 1 equals 9 minus 3 equals 6. So we could have 6 options for step 4. Or if 0 was not chosen, or if 0 was chosen, excuse me, in steps 2 or 3, then this minus 3 turns into a minus 2. And we have 9 minus 1 plus 1 equals 9, minus 2 equals 7, actually. So we potentially could have 7 options for step 4. So because this depends on the previous steps, we should reframe the multiplication rule attempt here. So attempt 3. Here we can have step 1 be the same, 4th digit. 4th digit, we know we have how many options for 4th digit? We have 5, 1 for each odd number. Step 2, let's have the first digit here. Where step 2 has 8 ways now. From 1 to 9, that's 9, minus 1 from the previous step for step 1 is 8. Step 3, let's call it the second digit. This has 8 ways total because we had 10, since 0 is inclusive, minus 2 from the previous steps. The final step, let's choose the third digit. This is 7 total ways because we have 10 total options minus 3 from before. That gives us 5 times 8 times 8 times 7 total options here. I highly recommend trying to do the same problem but for even numbers. How many even numbers from 1000 to 9999 have distinct digit? This is different from the previous problem. I highly recommend trying this. Next lecture, we will introduce the idea of permutations of distinct objects.